Okay, now the thing which I want to discuss today is a fine, what should I say, an explanation to existence and non-existence of solutions to elementary Diophantine equation. Okay, what I must recall at least a little bit is what a Diophantine equation typically looks like. Okay, so this is something called a linear Diophantine equation, where we solve equations of the form ax plus by is equals to c, where a, b, c are integer coefficients and x and y are identifiers, which will still consider values from integers once we try to find a solution. Or rather, I mean it in this way, that if I want to find solutions for given a, b, c to this equation, then the solutions must be strictly integral. That's what I want to talk exactly. So this is called a linear Diophantine equation. Linear Diophantine equation. On a similar note, and you can also write it in this way as well. One form is also in this form, ax plus by is equals to cz. This is also one form. Sorry. Okay, this is also one form. So xyz will be also there. Moreover, we can also sometimes define what's called an nth degree Diophantine equation. Which we often define as a x to the power n plus b y to the power n is equals to c z to the power n. Okay, where again a, b, c are integer coefficients, and if we want to find a solution to this equation, then the solutions must be strictly integral, and if we can't find integral solutions, then we simply say that this equation has no solution. So we are going to discuss a similar quadratic Diophantine equation of the form x square plus y square is equals to 3z square. And what I want to do is that I want to find solutions to this. I want to find integral solutions to this Diophantine equation. Okay. So now the first thing first, which we can clearly observe out from here, is that if I consider x to be 0, y to be 0 and z to be 0, then we get what we call a trivial solution in this case. Okay, or rather I can also use the term a zero solution. In this case. So what I want to discuss is that whether I can achieve any non-zero solution. Okay, clear? Now what we do is that we consider a very simple case. What we do is that suppose we have integral solutions. Okay, first thing first, what we want to do is that let me write, we can assume that x, y, z have no common factors. Okay, the GCD of them is 1 in some terms, because if they have a common factor, say d, then I can just cancel out d squared from both sides of this equation, and then we will be reaching a reduced form of the same Diophantine equation, where we get the reduced values of x, y and z will be mutually coprime, right? So in a way we can simply assume them to be coprime at the very first point. So we start with this assumption. Okay, now suppose a solution, I should say an integral solution, exists to, let me just name it as 1. Okay, to 1 and let me frame it as star after assuming star, let's say after assuming star. Okay. Okay. Now so we are gonna evidently use ring theory. So I'll obviously assume that you have some basic knowledge in ring theory. That the concepts which we will be using in this lecture, it will be very minute, but the specific thing which we are going to discuss for a solution in this case is the concept of a reduction homomorphism. Okay. What is a reduction homomorphism? Typically what we are trying to do is that, so let me write it like this, the concept of a reduction homomorphism. The concept of a reduction homomorphism. So typically what I am trying to do is that I am trying to reduce Z modulo n. In some sense, let me talk it in this way. See, I have Z to be of this form, right? 0, 1, 2, and it goes on, minus 1, minus 2, and it goes on. Okay. What I want to do is that, suppose I want to discuss about some property which is related to integers, but examining that property by considering each and every integer is quite a cumbersome process, right? Because there are infinitely many. So in a way what we try to do is that we want to reduce Z to some structure which is evidently finite, and hence we get a smaller number of elements to examine the same property. And for that what we need to do is that we need to preserve the structure of Z and we need to reduce it down to finite number of elements. And what should be the exact procedure to do so? We know that provided Z, for any integer you choose, nz is an ideal. Nz is an ideal, right? If nz is an ideal, then we can talk about the quotient group Z mod nz, which will precisely consist of values of Z reducing it to modulo n. So it will be typically considering values 0, 1, 2 till n minus 1. Moreover, what we can do is that we can apply what we call the canonical projection, which is a ring homomorphism in this case, from Z to Z mod nz, where we send an element A to A plus nz. Okay. Typically what is happening here is that we are preserving the structure of Z and still we are reducing it to some element, I mean to say to some group which is much smaller in size. Hence examining certain properties of integers can also be examined through using the elements of Z mod nz by virtue of this canonical projection with a less strenuous effort, right? Now in this case observe, so this is the basically concept of a reduction homomorphism, and what we say here is that we are reducing Z modulo n. So this process is typically termed as reducing Z modulo n. Okay. Now if there exists integers satisfying 1 and star, then we call those integers to satisfy the Diophantine condition in this case. Diophantine condition 1. Okay. But then this gives us a relation between them, which is strictly obeyed by 1 between them. What I mean to say is that if I get hold of integers x, y, z which satisfy 1 and star, then there exists a relation between them, between x, y, z, such that x square plus y square is equals to 3z square. So if there exists a relation between them, this implies there exists the same relation between them between them considering the reduced ring of Z modulo n for any n. What I mean to say is that if x square plus y square is equals to 3z square in Z, then x square modulo, I mean to say it in this way, then x square mod n plus y square mod n will be equal to 3 times z square mod n, and this whole will also be happening in modulo n, so I can write it like this. Okay. So this property will also be carried over to the reduced ring of Z, and by reduced ring I mean the quotient group Z mod n Z, quotient ring Z mod n Z. Clear? But since this can happen for any n, we can simply talk about n being 4, right? So let n be equals to 4. If n is equals to 4, then observe that now for any integer you choose, for any m, we know that m is congruent to either 0 or 1 or 2 or 3 modulo 4, but that simply implies that if I talk about m squared, then it will be congruent to 0, 1 squared, 2 squared or 3 squared modulo 4, but then that's simply 0 or 1 modulo 4, right? Therefore, if we get hold of integer solutions to the given Diophantine equation, then since this property will also be carried over to the reduced Z modulo 4, then I can say that if x square plus y square is equals to 3z square in Z, then let me just write this as 3, then 3 holds for n is equals to 4. But if I use n equals to 4 in 3, then x square modulo n can either be 0 or be 1, y square modulo n can either be 0 or be 1, and similarly z square modulo n can either be 0 or be 1, right? Therefore, we have the set of elements 0 or 1 plus the set of elements 0 or 1 to be congruent to the set of elements 3 times 0 or 1. So 3 times 0 will be 0 and 3 times 1 will be 3 modulo 4. But then observe, if all these, the only possibility for this to hold is if we have all zeros. Okay, suppose let me say, suppose we have 0 here, we have 1 here and we have 3 here. Will it satisfy the equation? 1 is not congruent to 3 modulo 4 clearly, right? So only I can assume value 0 on the left hand side. On the right hand side, if I assume 3, 0 is not modulo 3, 0 is not 3 modulo 4, therefore 3 cannot be a possibility. The only possibility is that 0 plus 0 is congruent to 0 modulo 4. But if that happens, that means that x square, therefore x square is congruent to 0 modulo 4, y square is also congruent to 0 modulo 4, and z square is also congruent to 0 modulo 4, which means x, y, z are all even, but that's a contradiction, which is a contradiction to star, because we had assumed that x, y and z are mutually co-prime. Therefore, one can't have a non-zero integer solution. Okay. Yeah. So that was again a short lecture where we sort of try to relate abstract algebra and elementary number theory. I try to bring out similar topics in future. So meet you guys in the next lecture.